All right, let's talk about throwing a ball. So what happens? You throw it up, it goes up, it comes down, right? So when I throw it up, there's a certain speed that goes up, and gravity pulls it back down, right? Okay, good. Now, as it happens, um, basically the height as a function of time is quadratic here. All right, so that's just a fact of local physics, you might say. Um, Gravity is just this constant force, and then through some magic of calculus, um, that constant force, because it's not changing very much where we are. It's not really constant, of course, but it's pulling it down in kind of quadratic fashion. Okay, now we could also throw it horizontal, right? This is giving all the speed here, and so basically, if I want to get over here, boom, right? I just throw in a straight line, right? That's good, right? Well, not really. So if I let it go like this, gravity is still pulling it down, so it's curving down like this. That curve is like a parabola, as we'll see. Basically, the parabolic pulling in time leads to the height going down like this, right? Okay. But it's still going like this. So it's got these two motions, right? It's got this horizontal motion, and then it's got this going down motion. And then that traces out this parabola. Okay. And you could also throw it at an angle. And again, so that angle, you can view it as kind of having a horizontal component that just goes whoosh, and a vertical component, which is again going to be like a quadratic. So it kind of goes so. So there's the angle, and then it comes down. Okay. So let's try a problem. So, I'm just going to tell you that basically h of t, the height, is, and this is in feet per second. Typically we do meters per second in science, but we like feet, huh? For now, it's minus 16 t squared. That's just kind of this gravitational acceleration. So that's gravity accelerating. And then we have kind of vt. This is the velocity up or down. If it's down, it goes negative. We've chosen, because we put a minus sign in front of the 16, down goes towards the Earth. And then plus starting height. Okay, so that's the basic height formula. And so this is height. That's why we have h. And then let's just say k of t vh is ek times t plus starting position. Okay, and this is velocity in horizontal direction. Okay, I may regret these names. Actually, could just call this x of t. Okay, more complicated. I'll just keep it k of t. All right. Okay. All right. So let's say that I'm throwing this ball, hacky sack, at an angle, and this thing. So I'm going, say, 40 feet per second to the right. We'll take that to be the positive direction. And we'll say I threw it up 20 feet per second. So these two different directions. And if you want to know the actual kind of thing here, well, that's our Pythagorean theorem, right? 20, 40. Oh, why didn't I say 30? I'll go with 30. 30 and 40. And so this is a 3, 4, 5 right triangle. You can do the Pythagorean theorem, 30 squared plus 40 squared, take the square root. Boom. We'll just go with it. So this is saying that I had this angle, whatever that angle is, and I launched it in such a way that it was going 50 feet per second in that direction. And then that decomposed, because of this angle, to 40 feet per second to the right and 30 feet per second upwards. And so h of t is equal to minus 16 t squared plus 30t. And we'll just say that, I don't know, what would you actually do? Kind of above the head, we'll just say 6 feet. Plus 6 feet, so that's 6 feet above the ground. And then this other direction, k of t, is, we've got 30t, and we'll just say that this, we'll just take that to be 0. That's my starting point there, so that's 0. Go. Maybe 1 or 2. I don't know. Okay. 0. 0 is nice. Okay, so now I've got these two things. What are some questions that I might want to know? When does it hit the ground? Okay. Where does it hit the ground? So if I figured out the time when it hit the ground, I could just plug that into the function k and get the answer. What else? How high does it go? How high does it go? Where does it? What is that height? And what does this trajectory look like? Okay. Well, so there are many questions going on here, right? So when does it hit the ground? So this is h of t equal to 0. Again, this is a quadratic, so there's two solutions. One's going to be negative, one's going to be positive. Parabola, so this is h of t, is going to look like this. Okay? So that's one parabola in this problem. And then there's also that max. So high does it go? So that's how high does it go? This is the max of h of t. Right? And what does the trajectory look like? What is that height? So basically get t of that maximum, then you plug it into k of t. Figure out this t, and that's, again, just plug that in. And now this trajectory, well, that's a little bit tricky. So the trajectory, we want sort of x, y, tracing around like the x and y. And so what is x? X was this k of t. So this is kind of like 30t. All right. And then the y is minus 16 squared plus 30t plus 6. Okay, so that's fine, except what? This is called the parametric equation, and one can graph these things involving time, gives you the x and y, but it's a little bit more complicated. Here we can do something tricky. X was supposed to be 30t, so t is equal to x over 30. So we plug in for the t here. We have x, and then we have minus 16, x over 30 squared, plus 30, x over 30. Oops, why am I having 30 there? One of these should be 40. K of t should be 40 of t. 40t, 40t, 40, x over 40, 40, 40, 40, 40. All right, plus 6. So that's the trajectory. So I had x equaling this 40t, because that's how far it travels horizontally. And so I just solve for t in terms of x. And then I can get rid of the t. It's nice like that. All right. So let's go and explore a little bit of this in GeoGebra. All right. So first of all, here's what the height function looks like. That's what the height function looks like. Doesn't stay up too long. Looks like, so extremum, you get that height. So 0.94 and 20.06. So basically, let me have this graph h of t. We have this height here, 0.94, 20.06. So the max height is going to be, how high does it go? 20.06. And the t is 0.94. So that's very important to keep in mind what the x-coordinate represents. Here it represents the time, and then the y is the height. And now that we have the height, we can also look at this other function, which is really kind of in its own realm. Has nothing to do with this parabola, except that now I want to find out where in that location it is. So this thing is k of 0.94, which is equal to 37.6. Okay, good. All right, whoa, so that was the height. Then there's the roots, where it intersects. So this is when it hits the ground, right? Now B, that's negative. And that's because, you know, you could flow the time backwards as if it had been, you know, falling from that height going the opposite direction, and that's where it would hit the ground if that was its trajectory. Obviously, it wasn't because I started it, but if I did this and then I reversed the time and removed my part in it, it would go past me and then hit the ground. So that's what that negative root is. Forget about it. The positive root is 2.06. Oh, obviously the height is 0. And so then K, what is this? I called it G. G 2.06. So that's about 82.4. So that's 82.4. And that's you know, it's, you know, this negative point here is pretty close to 0. So it's almost the case that the height, the midpoint here of H is it is halfway between B and C, but because B is so close to the origin, it's almost halfway, so you can almost kind of double it to get to C, close to C. It's not quite true, but it's almost true. And so they're kind of roughly. So 2.06 is almost twice 0.94. And twice 37.6 is not too far from 82.4. Some differences, but it's close. All right. Next up is plotting this trajectory. Let me just clear everything off. Oh. Okay. So I claimed that if I plugged in x over 40, so squared plus 30 times x over 40 plus 6, that would give me a trajectory. Okay, zoom to 15. This is the actual xy trajectory. So this is time stripped out of the equation. And now let's get these roots. E is 82.29, which is close to what we saw before. And the extremum here is 37.5. The wibbly wobbly differences is probably because I didn't actually plug in the solution from the other stuff. I kind of rounded there, so it gets a little. So these are the actual coordinates, unless I made a mistake somewhere, but pretty sure this is looking about right. So anyway, that's the XY, that's the actual path of the ball in space. But it doesn't tell you when it's traveling. We've stripped that information totally out. And that's okay. That's all you care about. And that's your problem. Now, you can do all this stuff that we've done with other stuff in terms of finding out, with algebra. So you can guess at these things and manipulate that. You can complete the square. and solve for things that way. You can use the quadratic formula for some of this stuff. I mean, obviously the vertex is more or less completing the square, but you know, you can do all those things. But hopefully that picture gives you a good start on these kinds of problems, sort of understanding how balls and stuff work with gravity, and you can now manipulate that and answer any question you want about them. All you need to know is basically the decomposition into how to decompose this vector here into these two things, or just, we haven't talked about that, but you can just be given the vertical and horizontal speeds, and then that's good. Okay. And I guess we're done.